Good morning, everyone. I'm just correct the name a little bit. Like my name is Parinya, and my professor is Daisuke Iwai and Kosuke Sato. Well, so in the morning sessions, you saw the keynote speaker already speak almost everything that we will talk today about this session. So if you not want to hear more, you just come to this talk. So actually, first of all, I would like to show this to a picture. So could you can distinguish between these two fabrics? Like which one is the polyester and which one is the cotton fabrics? Okay, everyone can know that, right? So the left one is the polyester, and the right one is the cotton fabrics. We might be difficult to see because by just looking at its appearance, because it's static fabrics, so it may be difficult to distinguish. However, if we look at its motions, it is more easier for us to distinguish the difference between fabrics with the different intensity. So such feature is usually called the bending stiffness. So previous works, Bowman in 2013 has been investigated this bending stiffness feature by estimating the fabric's motions from its uniform movements using the computer vision techniques. The results compare with the human observations on the same fabrics, and the results conclude that the humans are good to estimate the flexibilities of the fabrics from its motions. And the different fabrics properties usually provide the different motion patterns. And so why such information is important for our AR, VR communities, especially for these research communities. This is because in our communities, several works have been attempts to simulate different behavior of the fabrics. Some works create AR system that simulate the texture and the color for the designs. While another works create the system for interactive design fabrics using the spatial augmented realities approach. However, the current technologies only focus to modify the appearance, such as the color, the texture, or the static material properties, but not allow to simulate the more different type of fabrics properties, such as the bending stiffness. So our work takes this challenge into account, and we try to find out the potential solutions to this problem. So we propose the techniques to modify the fabric's properties that turn the cotton fabrics to the different type of fabrics, such as polyester, aligning without refabrications using the spatial augmented realities. We call this system FleXeen, and as you can see from this example, our prototype system can turn the physical cotton fabrics to the virtual polyester by projecting the enhancing the bending stiffness. So we realized this idea by considering the optical flow of the moving fabrics based on the suggestions from the Bowman et al. Works in 2013. We call this method the flow enhancement. So our method is simply consists of four steps. First step, we capture the original movements of the fabrics in order to remove the distractions from the projection image and the original moving fabrics. We apply the near-infrared camera that only capture the near-infrared near-infrared image, so that the projection image that projecting on top of the original fabrics is not captured into the framework. Then we estimate optical flow from the local feature by using the dense optical flow proposed by Fernbach in 2003. And since we use the white fabrics that allow to reduce the visual cues from the fabric's texture, it is difficult to detect the local feature on the fabrics. Fortunately, we found that the wrinkle items around the fabrics is enough to detect the optical flow in these patterns of the fabrics, so that we use these informations for create a displacement map in our proposed method. So we then multiply the motion flow obtained from the dense optical flow algorithm with the specific perception value that we will talk in the next few slides to enhance the motion flow. And then we remap the current capture frames with enhanced displacement motions and superimpose back into the original fabrics. And all the process are in real time and within 60 frames per second. And here is the results comparing with the original moving fabrics. And maybe it is difficult to see. Here it shows another example that obtained from our proposed method. by breakdown into the frame sequence. As you can see here, the flow enhancement provide the higher motions comparing to the ones without flow enhancement. And for more details, please see the paper. And we conduct a psychophysical experiment to find out the parameters that allow to modify the bending stiffness and the perceived difference fabric characteristics. So 21 participants, including 17 male and 4 female, were participated in the experiments. We used the subjective magnitude estimations method to compare its parameters. We render the fabrics with the flow enhancement projections in advance by using the prototype system displayed on the LED display. And for more details about the capturing process and the flow of the experiments, please see in our paper. The display shows the reference fabrics on the left and the stimulus with the flow enhancement projections on the right. Both are played at the same time. We asked the participant to rate whether the left fabrics or the right fabrics is more flexible, and if the answer is the right side, so the answer should be, they should be estimate the value more than 100. And the results show that by enhancing the fabrics with the flow enhancement parameter between 0.2 to 7.0, it is possible to manipulate the fabric's bending stiffness that modifies the perceived fabric characteristic, different fabric characteristics. Sorry. For more information, please see our paper. And from the results, we then create the computational model that derive the best parameter for the flow enhancement to accurately manipulate the perceived bending stiffness. We applied linear regressions since it is simple parametric functions for approximated data in our method. We then create applications to validate the computational model that we obtained from the psychophysical experiment. We call the applications very simply is curtain applications. So which allow to simulate the different type of fabrics characteristics with either the air generator or the user interaction. For the air generator, the airflow is blown from the bottoms of the fabrics to generate the movements of the non-periodic motion. And for the user interactions, user can directly interact with the fabrics, and at the same time, the system automatically create the different type of fabrics based on the computational model. We conduct the validations of our obtained computational models by using the magnitude estimation, similar to what we did in the psychophysical experiment. The participants were asked to watch the reference fabrics in the motion display and interact or observe the application fabrics, then compare the estimations to estimate the magnitude of the stiffness. We use 3 different types of fabrics, including polyester, the cottons, and the mixed linen and cotton fabrics to find out the capabilities of the proposed computational model. Those 3 types of fabrics provide the different ranks of the bending stiffness from the most flexible, like polyester, to more stiff, like the mixed linen cotton fabrics. So the results show that our proposed computational models could manipulate the perceived stiffness with an average accuracy about 90.3% within the ranks of the fabrics from polyester, cottons, to the mixed cottons and linen fabrics. For example, when we project the small flow enhancement projections value to reduce the stiffness of the fabrics, the results show that the participants perceive the fabric stiffness similar to the target perceptions that predict by our computational model, especially for the user interactions. However, we found that with the airflow, we have show some error when we apply the techniques with the airflow, especially for the mixed linen cotton fabrics. And for more discussions, please see our paper. So let me conclude my talk. And in this work, we present the new method to manipulate the perceived stiffness of the fabrics using the spatial augmented realities. In particular, we propose the flow enhancement projections that work in real time. And our proposed system allows the user to accurately control the perceived bending stiffness with 90% of its accuracy from the ranks from the polyester to mixed cotton linen fabrics. Of course, there is still very small ranks of the fabrics that we can simulate and we can change. However, this will be considered in our future works. And it is the grants we support our works by JSPS Kakeni, and we would like to also thank the all participants that participate in our experiments. And for more information, you can see in our website, you can search FleXeen Osaka, and you can find more information, including this, all of this slide of the talk. And this is all of my talk. Thank you so much.
Great. Do you have any questions from the audience? Can you come to the microphones and just identify yourself as you
Hello, my name is Ekta Jain from University of Florida. This is very, very interesting work. Thank you very much for presenting it.
Thank you.
I just was curious as to what were the kind of applications that you had in mind when you were doing this. This is almost like magic, right? So what were the applications you were thinking of?
We're looking for something like your fashion shows. For example, like you wear only one clothes, and you go into the podiums, and you walk around, and then you use the projection mappings that dynamic capture and tracking the humans, and then you change the different type of fabrics. So more high level is like design application.
Okay, I can imagine that kind of e-retail. Okay, thank you.
Hi, I'm Long Pan from National Taiwan University. Really interesting work, I really like it.
Thank you.
Yeah, so I'm just wondering if you have thought about to simulate like liquid instead of fabric.
Liquid, yes, liquid is interesting for many research in this field, I think.
Yeah, I'm just wondering if you can actually make people like think this is not just like normal fabric, but it's actually like watery texture. No, just like
yes, it should be
idea.
considered in our future work.
Cool.
Great. I have a final question for you. How did you decide this placement here? How did you decide what was the best way to pull the fabric to show the thickness?
So we try with we try several times in several positions. So it's just our if we say in research, we call it this preliminary experiment. But if we call it in general, we just, okay, let's say this is a good position. We just, okay, this is maybe nice ways to pull the fabrics. So what we pull is actually on the two sides with the two servo motor, and we're just pulling on the left and right simultaneously using the Arduino stuff.
And do you have any intuition on if you pulled it in a different way, how that might affect the perception of the stiffness?
That's interesting questions. Yes, we should try also in our future work, yes.
Lots of future work.
A lot of things to do.
Paper,
yes,
right?
because it's like yes.
Yeah. Well, great job in presenting it to us in 10 minutes. Thank you very much.
Thank you.